Today we shall study about some important aspects of electric field. The first is the electric field due to charge q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. The charge q which is producing the electric field is called a source charge, and the charge q which tests the effect of source charge is called a test charge. Note that the source charge q must remain at its original position. However, if a charge q is brought at any point around q itself is bound to experience an electrical force due to q and will tend to move. A way out of this difficulty is to make q negligibly small. The force F is then negligibly small, but the ratio F by q is finite and defines the electric field. E barabar limit q tending to 0, F by q. That is equation number 1. Second, note that the electric field E due to q though defined operationally in terms of some test charge is independent of q. This is because F is proportional to q, so the ratio F by q does not depend on q. The force F on the charge q due to charge q depends on the particular location of the charge q, may take any value in the space. Depends on the particular location of charge q may take any value in the space around the charge q. Thus, the electric field electric field E due to q is dependent on the space coordinate r. For different position of the charge q will over the space, we get different value of electric field E. The field exists at any point in three-dimensional space. For a positive charge, the electric field will be directed radially outwards from the charge. On the other hand, the source charge is negative. The electric field vector at each point points radially inwards. Fourth, since the magnitude of the force F on charge q due to charge capital Q depends only on the distance r of the charge q from the charge q, the magnitude of electric field E will also depend only on the distance r. Thus, at equal distances from the charge q, E will also depend only on the distance r. Thus, at equal distances from the charge q, the magnitude of its electric field E is same. The magnitude of electric field E due to a point charge is the same on a sphere with the point charge at its center. In other words, it has a spherical symmetry. Now, the physical significance of the electric field. For electrostatics, the concept of electric field is a convenient but not really necessary. Electric field is an elegant way of characterizing the electrical component environment of a system of charges. Electric field at a point in the space around a system of charges tells you the force a unit positive test charge would experience if placed at that point without disturbing the system. Electric field is a characteristic of a system of charges and is independent of the test charge that you place at a point to determine the field. The term field is in physics generally refers to a quantity that is defined at every point in a space and may vary from point to point. Electric field is a vector field since force is a vector quantity. The true physical significance of the concept of electric field emerges only when we go beyond electrostatics and deal with the time-dependent electromagnetic phenomena. Suppose we consider the force between two distant charges q1 and q2 in accelerated motion. Now the greatest speed with which a signal or information can go from one point to another is c. The speed of light. Thus, the effect of any motion of q1 and q2 cannot arise instantaneously. There will be some time delay between the effects, the forces on q2 and the cause motion of q1. If it is precisely here that the notion of electric field, strict electromagnetic field, is natural and very useful. The accelerated motion of charge Q1 produced electromagnetic waves, which then propagate with the speed c reach Q2 and cause a force on Q2. The notion of field elegantly account for the time delay. Thus, even though electric and magnetic field cannot detected only by their effects, forces on charges, they are regarded as physical entities, not merely mathematical constructs. They have an independent dynamics of their own. It means they evolve according to laws of their own. They can also transport energy, thus a source of time-dependent. Electromagnetic fields turn on briefly and switched off, leaves behind propagating electromagnetic field transporting energy. The concept of fields was first introduced by Faraday and is now among the central concepts in physics. Now the electric field lines, as shown in the figure, let us try to represent due to point charge pictorially. Let the point charge be placed at the origin, field at a point charge as shown in the figure. Now, is strong near the charge, so the density of field lines is more near the charge and the lines are closer. Away from the charge, the field gets weaker and the density of field lines is less, resulting in well separated lines. The picture of field lines was invented by Faraday to develop an intuitive non-mathematical way of visualizing electric fields around charge configuration. Faraday called them lines of force. This term is somewhat misleading, especially in case of magnetic fields. The more appropriate term is field lines, electric or magnetic. Electric field lines are thus a way of pictorially mapping the electric field around a configuration of charges. An electric field line is in general a curve drawn in such a way that the tangent to it at each point is in the direction of the net field at that point. An arrow on the curve is obviously necessary to specify the direction of the electric field from the two possible directions indicated by a tangent to the curve of a curved line. A space curve, it means a curve in 3 dimensions. The field lines around a system of two positive charges, QQ, give a vivid pictorial description of their mutual repulsion, while those around the configuration of two equal and opposite charges, Q minus Q, a dipole, though clearly the mutual attraction between the charges. If it has some general property, field lines start from positive charges and end at negative charges. If single charges, then start or end at infinity. It is taken as continuous line or curve. The field lines can never cross each other. Fourth, electrostatic field lines do not form any closed loops. These are the properties of the electrical field lines. The nature is conservative. So it is a conversion of charges as shown in figure A, B, C, D. The first figure is when charge is going from the point charge, when Q is greater than 0, when coming Q is smaller than 0, and repulsive charge force, then Q plus Q both are same, and the charges are different, plus Q or minus Q, then attractive force.